Welcome to week 8, lecture 3. We're going to talk about kinetic energy. So this comes from chapter 11-4, 6, and 8. It's work done by a variable force first, so that part's not about kinetic energy. And then we have kinetic energy and an example, and kinetic energy and collisions and an example. So work done by a variable force. Before we learned about work but that was work done by a constant force. So the force wasn't changing, but that's not always the case. So when the force does change over the distance, we have to take the integral. So let's look at an example of a variable force first. The spring force is a variable force. It's given by this equation up in the corner. Here. The spring force equals negative kx, where k is a spring constant. So that's just a property of the spring itself, kind of how easy it is to compress or stretch. And x is the displacement from the relaxed length of the spring. So springs have a natural or relaxed length that they just sit in when they're not actively being stretched or compressed. And the further the spring is displaced from its natural length, the stronger the spring force is. And that force acts to oppose the change in length. So if the spring is being compressed, like on this side, the force is acting to push it back push it back out to its relaxed length. Or if it's being stretched, then the force is acting to pull it back to its relaxed length. So let's take a look at work done by a spring force. Okay. So the spring force again is this negative kx. And then the thing we just saw work done by a variable force is the initial x, final x, the force, which is the spring force in this case, dx. So now we can plug in our equation for the spring force into our derivative, or integral, sorry, negative kx dx. And the integral of x dx is just x squared divided by 2. So I'm going to pull the k out since it's we have x squared over 2 from x initial to x final. And that becomes, and this time I'm pulling the half out, negative k over 2 times x final squared minus x initial squared. So the work done by a spring force is negative 1/2 k x final squared plus x initial squared. 1 second. Okay, I just had to check. I just copied that part wrong. So yeah, it's still negative there. And then a simplified version is if we start where x initial is 0, so that means that it starts at its relaxed point. Then it just goes to x. We can write the work done like this. Work by the spring equals negative 1/2 k x squared. So that's just a tiny sample of what it's like to find the work done by a variable force. Now let's go back to the slide. Okay. Now let's think about a situation where a car is being towed. It starts out with an initial velocity. A force is applied to it over a distance, and then it has a new final velocity. So a force acted over a distance, which we know means work is done. But what does it mean that velocity also changed during that process? So what happened is that the work done resulted in a change in the kinetic energy of the system. The kinetic energy is the energy of motion given by 1/2 mass times the velocity squared. And I didn't like any of the ways I found that this equation was derived. So I'm just giving you the equation and not the derivation of it. The textbook does have a derivation if you want, but again, I just didn't really like it. Didn't think it helped that much, but depends on you. So what we have is that the work done, because again, the work is that force applied over that displacement. The work done is equal to the change in kinetic energy of the system, and the kinetic energy is 1/2 mv squared. Now we're going to do an example of this, but I'll read it to you first. An old canal boat, 55,000 kilograms, is pulled by draft horses. The horses pull with a steady force of 1,400 newtons. How far do they have to pull to get the boat up to 0.7 meters per second? And just to note, this example does not come from your textbook. Okay, so let's write down some things. So work is equal to FD cosine theta. It's also equal to the change in kinetic energy. And this question asks us how far they need to pull the boat for it to get up to a certain speed. So we want V in this example. And you can see that the force and the distance displacement are parallel to each other. So that gives us 1 for the cosine. So we just end up with FD equals the change in kinetic energy. And I'm just going to start us out by finding the change in kinetic energy. So that is the final kinetic minus the initial kinetic. And those are 1/2 mv final squared plus 1/2 mv initial squared. It starts at rest, so that goes away. So we just actually have the final kinetic energy, which is 1/2 mv final squared, and we can plug in our numbers. So 1/2 55,000 kilograms times 0.7 meters per second, whole thing squared. And that gives us 1 second. Okay, I didn't have my numbers up, so I need to grab them. So that gives us a change in kinetic energy of 13,475 joules. We could round that, but I'm going to leave it as that for now. Okay, and then let's go back to this relationship here. FD equals change in kinetic energy, and we want D, so we're just going to divide that force on both sides. Gives us the distance is the change in kinetic energy divided by the force. So let's plug stuff in. 13,475 joules divided by 1,400 newtons. Yeah, 1,400 newtons. And this gives us 9.6, or I'm going to round here, 10 meters. So that's the distance they need to pull the boat to get it up to that speed. So just real quick, we wanted to know how far the horses had to pull with a specific steady constant force to get the boat up to a certain speed. And we know that the work is both FD cosine theta and also equal to the change in kinetic energy. We found the change in kinetic energy and then solved for the distance and found it to be 10 meters. Let's look at these examples of, right now it's just this example of collisions. We have 2 frames here that we're looking at. There's the laboratory frame, so just like a frame that isn't accelerating, and the center of mass frame, which is a frame where the center of mass isn't. So we have our initial situation in the lab frame. where mass 1 is moving with an initial velocity and mass 2 is at rest. In the center of mass frame, both masses are moving toward each other with initial velocities. We have an elastic collision where the masses collide and bounce apart. In the center of mass frame, they bounce off with momentum equal and opposite to their initial momentum. So what we have in our two frames and that kinetic energy brings in is that the kinetic energy of the system, so when we talk about system in these kind of collisions, it's both objects that are colliding. So the kinetic energy of the system in the laboratory frame is conserved. Sorry, I want to turn on the laser pointer. There we go. The kinetic energy of the system is conserved, but in the center of mass frame, the kinetic energy of each mass is conserved. So, for example, mass 1 has the same kinetic energy initial and final, and same with mass 2. And you can see this by their velocity vectors being the same side, just opposite directions. But in kinetic energy, the velocity is squared, so the sign doesn't matter. Now, in an inelastic collision, we find that some energy is lost. So the final kinetic energy of the system is less than the initial kinetic energy of the system. And we can see this by their vectors being smaller, just like slightly smaller than the elastic ones. In a completely inelastic collision where the objects stick together, things like balls of clay, in the center of mass frame, they aren't moving because the center of mass isn't changing position. Like they're together. And in the lab frame, they move together with a final velocity. So in a completely inelastic collision, we have maximum energy loss while maintaining conservation of momentum. So momentum is still conserved, but we lose the maximum amount of energy we can while maintaining that conservation of momentum. And finally, an explosive collision, the total kinetic energy of the system is less than the final the total initial kinetic energy of the system is less than the total final kinetic energy of the system. That's what makes it explosive. Let's do an example where with kinetic energy and collisions. So let me read it. On an air hockey table, a moving puck traveling to the right at 2.3 meters per second makes a head-on collision with an identical puck at rest. What is the final velocity of each puck? Okay, let's break this down into two parts. So this is a perfectly elastic collision, which means both momentum and kinetic energy are conserved. So let's start with momentum. Momentum, so P1 initial plus P2 initial equals P1 final plus P2 final. But initially, mass 2 is at rest, so that goes away. And let's plug in what these are. So mass 1 V initial equals mass 1 V final plus mass 2 V final. So if we didn't have the option of using conservation of kinetic energy here, we would not have enough information because we don't know what either velocity is. Oh, sorry, I should also 1 and 2. So we need another equation. Conveniently, we have one. Kinetic energy is conserved. Conserved. And I'm still going to write this part. So kinetic energy of 1 initial plus kinetic energy of 2 initial equals kinetic energy of 1 final plus kinetic energy of 2 final. And again, velocity of mass 2 initially is 0. So we end up with 1/2 mv1 initial squared equals 1/2 mv2, oh, sorry, v1 final squared, v1 final squared plus 1/2 mv2 final squared. And sorry, these masses should also have subscripts specifying which ones they are. So I don't know. Oh, I guess they have the same mass. So that'll make it a little easier for us. Okay, next up, now that we have our two equations and our two unknowns, these guys, and technically we don't know the mass either, but I just said the masses are the same. So let's look at what that means. I'm just rewriting the momentum. Oh, see, still trying to give it a subscript equation, and I'll rewrite the kinetic energy equation with our masses that are the same, but that mass is in each term, we can divide it out. So it doesn't matter that we don't know the mass because it's the same and it cancels out. So the same thing happens with kinetic energy squared plus 1/2 m2 squared. Okay, all those masses cancel. And also actually in this equation, the 1/2 cancels because they're in each of them. So that gives us simpler equations. That gives us v1 initial equals v1 final plus v2 final, and v1 initial squared equals v1 final squared plus v2 final squared. Okay, now we just figure out how we want to plug or combine these equations to solve. So I think we'll just solve this equation, for one of these velocities and plug it into this equation. So what that looks like, we'll start here, v1 final plus v2 final, and then I'm just going to subtract v2 final on both sides. So I end up with v1 final equals v1 initial minus v2 final. And then I can plug that in here. So v1 initial squared equals v1 initial minus v2 final squared plus v2 final squared. So then we have to factor this out. I'll put it right here, v1 initial squared equals, so just for completeness, if you are totally comfortable with factoring, then you can just move on to the next part. But if you aren't, I'm just going to quickly show. So, reminder, we multiply the first terms together, we multiply the second terms together, and then we multiply the first and last and the second and first. Sorry, BOIL actually stands for something. But don't worry about that part. So this is what it comes out to, which is, so this one is just v1 initial squared. And then this one is plus v2 final squared. And then this one is minus v1 initial, v2 final. And this one is the same thing. Minus v1 initial, v2 final. Okay. And then we have v2 final here and v1 initial. These are squared. Okay, now let's subtract this from both sides, which just ends up with 0 on the left side. And then we will combine these like terms. So 0 equals 2v2 final squared minus minus 2v1 initial v2 final. Cool. And now, just like we did with our original equation, we can cancel out the 2's and one of the v2 finals. So we end up with 0 equals v2 final minus v1 initial. And we can just add v1 initial to both sides, but this gives us v2 final equals v1 initial. And 2.3 meters per second is what that was. So the final velocity of the second puck is 2.3 meters per second. And if we go back to this equation, we can find the final velocity of the first puck. So we have v1 initial equals v1 final plus v2 initial. Final, I mean. But so to solve for v1, we just subtract this from both sides. But we just found, so v1 initial minus v2 final equals v1 final. But we just found that these guys are equal to each other. So this is 0. So the final velocity of puck 1 is 0. So just briefly, we could not have solved this problem with only momentum conservation, because we had one initial velocity and two final velocities. Well, one initial velocity we knew, and then two final velocities we didn't know, and one equation. So we needed the kinetic energy conservation equation also, and then the rest was really just algebra. And we end up with what actually happens is the first puck gives all its momentum to the second puck. Yeah, so that is this example and this lecture.